So welcome to this is the Further Maths Support Programme online revision session for AQA Statistics 1, and in this session we're going to be looking at the normal distribution. So when they ask these questions, normally they ask quite a lot of this in one question, so they're quite interested in assessing the properties of the normal distribution. You're expected to be able to use the table to calculate probabilities, and you're expected to work backwards to find means, variances and standard deviations of a normal distribution. So you're given quite a lot of information on the sheet. We're told that the mean is called mu, and we're told that the variance is called sigma squared, and we're also told that the probability density function is this rather beastly looking grisly thing. You're not expected to use this, okay? It's there for information more than anything else, but what it does tell you is how the normal distribution is set up. So we would generally call this as x. So, this is quite a lengthy question, and it covers most of the aspects that we need to look at. So here we go. The volume of shampoo, V, millimetres, delivered by a machine into bottles may be modelled by a normal random variable with mean mu and standard deviation sigma. And we're given that mu is 412 and sigma is 8. So what we can do here is we can express that V can be modelled as a normal distribution with a mean of 412 and a standard deviation of 8. Now, can I suggest that you always write this as something squared? So don't write it as 64, write it as 8 squared. It avoids some potential problems later, which I'll explain as we go along. So, when you're using the normal distribution table, the first thing I suggest is that you always make sure that you have what's called a left probability. So in other words, you're looking for cumulative probabilities. That's going to make life a lot easier. And the idea is we use a formula to standardize our distribution so that we can use this table. So here is your standardizing formula. Okay, so in this particular case my z value is going to be x, which is 400 in this case, minus mu, which is 412, divided by the value of sigma, which is 8. So what turns out here is that my value of z is equal to 1.5. Okay, so what that means is my question here can now be rewritten as it's the probability, negative 1.5. It's the probability of z being less than negative 1.5 is what I'm trying to find. Now there's some observations we need to take into account here, and that is symmetry. Now we don't have a negative z value, so we need to change this into a positive z value. And what we recognise is being less than minus 1.5 is the same as being more than positive 1.5. So there's lots of ways of dealing with this. So let's do it step by step. That's what we're claiming. Well, again, this is now the same as 1 minus the probability of z being less than 1.5. And we can now look this up in the table. So 1.50 is what we're looking for. So there's 1.50. And that gives me that probability there. So to calculate this, it's going to be 1 minus 0.93319, which is going to give me a value of 0.06, 0.0066 or 67, depending on your accuracy and things like that. We'll work that. Okay, so let's look for this part anyway, how the marks are allocated. So you're going to get 1 method mark for indicating a standardization. So if you're doing a correct standardization, you're going to get M1. Okay, now let me just emphasize the reason I've written this as 8 squared is because I'm going to use the 8 at the bottom. If you write 64, some students write 64 by mistake, so it's a safe way of doing this. Okay, your next method mark is setting up your situation in such a way that allows you to use the standardized normal tables, and then of course you're going to get your accuracy mark for the correct answer. Okay, so moving on to part 2, this time we're looking at V being greater than 420. So again, we could standardize, so Z is equal to 400. That's 420, that's your value of x, minus 412, that's your mean, over 8. So in this instance, z is equal to 1. So we can rewrite this as the probability as z being greater than 1. So again, we need to turn this around because it's greater than. So this is 1 minus the probability of z being less than 1. That's where your first method mark is triggered. So now we're just looking this up in the table. So 1 corresponds to 0.84134. So this is going to be 1 minus 0.84134, which is going to give me a value of 0.158 or 159, again depending on accuracy, and that's where you're going to get your second mark. Sorry, this is a B mark, as is this one. Okay, so that's quite nice. Now this one's only worth 1 mark, so there's an indication that something interesting is here. Now, an exact value on a continuous distribution is always 0, because if you think about it, area is probability. So if you just got a line at 410, what's the area of that line? Well, it's 0. Okay, so it's very important that you are fully aware of that. So part B. So this is an interesting one. A new quality control specification requires that the values of mu and sigma are changed so that the probability of Z being less than 400 is 0.05 and being greater than 420 is 0.1. And what we've got to do is show that these two equations are true. So let's look at equation 1 first of all. Okay? So what we need to realise here is we're given a percentile P. Now, something I want you to bear in mind is if your cumulative probability is less than a half, when you come to unstandardize it, it's going to give you a negative Z value. So I'm going to use that first of all. So I know Z is negative. Okay, so what does that correspond to? Well, let's consider this, 0.05. Well, 0.05 doesn't exist in the table, so what we do is we look at 0.95 instead, and we use the negative Z value. Okay, and that's because of symmetry and complements. Here, we're dealing with the top 1%. So whatever we do, I know that the Z value must be positive. So 0.99 is going to give me a Z value. I'll do that in a different colour. It's going to give me a Z value, I'll do it down here, of positive 2.3263. T263, and we can see this is going well because look, there are my values there, so we know we're onto the right tracks. So let's go back to equation 1, and what we've now got to do is to standardize this. So we've got to realize that this is the same as x minus mu over sigma, and we can now see very, very clearly that that's going to give me 400 minus mu is equal to negative 1.6449 sigma as required. Yay! Which is great. And then we do the same for the second equation. So here we're going to have the situation that 420 minus mu over sigma must equal 2.3263. So there is my second equation. So what we're required to do now is to solve this simultaneously, okay, for your final 3 marks. Now, the way that these work is it's much, much easier to do elimination than it is to do anything else, because you'll always have just, well, mu. Okay, so it's always by far the best way of doing these. So if we consider subtracting, that's going to give me 20 is equal to these two values subtracted from each other. Okay, so if we subtract them, it's going to give me 2.3263 plus 1.6449 sigma. So we can work that through by dividing, and that's going to give me a value of 5.04. So once I've got sigma, I can then substitute that back in. So 400 minus mu equals minus 1.6449 times by 5.04. And again, it doesn't matter which one you substitute it in, but that will lead you to a value of mu of 408. So let's look at how all the marks are allocated for this question. So your 3 marks to start off with, it's a show that. So we need to make sure we're doing everything. So by showing that these, the negative 1.6449 and the positive 2.3263, that's going to trigger a B mark. Now you only need one of those for that to trigger, but it's required. For a clear use of standardizing, you're going to get M1. Okay, and then if both equations are correctly derived without any steps missing, because it is to show that, you're going to get your final accuracy. And then for part 2, you're going to get a method mark for starting to solve the simultaneous equation, and then an accuracy mark for each of those correct. Okay.